Magee, and he will talk about convergence of unitary representations.
Thank you very much for the chance to be here. It's been a great conference. Yeah, so today I'm going to talk about convergence of unitary representations. The type of convergence that I'm going to talk about is extremely related to spectral gap. Okay? So it fits well with the conference, and it is in some sense a continuation of Ramon's talk. So let's start to talk about basic things. What is a unitary representation? What groups am I going to take representations of? So mostly I'm interested in infinite discrete groups. And any infinite discrete group is interesting to me in the context of this talk. So good examples: free groups, surface groups, hyperbolic three-manifold groups, SL3Z, braid groups. You can think of your favorite type of groups throughout the talk, that will work. UN is n by n complex unitary matrices. And what I think we should eventually try to do is to understand every finite dimensional unitary representation of our group. I think this is a good idea. But it's too difficult, basically. For example, if you have a hyperbolic three-manifold group and you fix n to be 2, like you land in extremely difficult topics. For example, the people who study that question, like when does a group have an irreducible two-dimensional representation? Sounds stupid, but they use very fancy tools like instant-on gauge theory. To study that, and for me this is far too difficult. Okay, so that's a good idea, and we should do it, but it's too difficult. So just to persuade you that it is a good idea, if you start to do this for the integers, you develop the Fourier transform. I think we all agree this is good. If we do it for Heisenberg group that Ozal mentioned, we get models of quantum mechanics, and these are very basic groups, but studying their unitary representations, we already got something extremely important. So like I said, fixed dimension is too difficult, so what I'm going to do instead is try to understand finite dimensional unitary representations as a dimension tends to infinity by comparison to limiting representation. I'm not exactly sure how to explain why, but the limiting representation for me it seems always to be the regular representation. That's interesting. So this is a representation that every discrete group has. You act on L2 of yourself by left translation. And that's a unitary representation. Now this is infinite dimensional. So even though I'm trying to understand finite dimensional things, I'm comparing to something infinite dimensional. Okay. So the type of convergence I want to talk about is strong convergence that Ramon mentioned. So yeah, if I have a sequence of finite dimensional representations, I say that they strongly converge to the regular representation if for every element of the group algebra, I extend my representation linearly to the group algebra. I have convergence of norms of that element. So, can I point? Oh yeah. So this is the norm in the finite dimensional matrix algebra, and this is the norm in the regular representation. They're operator norms. I do have to take linear combinations here, or else I just get a stupid, this is always 1. Okay, so if this is a group element, this is 1. So to get an interesting definition, I have to take linear combinations, right? That's strong convergence. Weak convergence is exactly the same thing, except instead of having the norm, you have trace. And then you can just take group elements because it is linear. So that's strong convergence and weak convergence. There's some gaps in my slide because I deleted all my probabilistic quantifiers. And that's actually kind of misleading. Okay, so we're going to come back to that point. But I could do that for this. Yeah?
PI are supposed to be non-commutative star polynomials, as in Ramon's talk?
Yeah, so good. That's a great question. It's like, so Ramon phrased things in terms of non-commutative star polynomials. But that's, from my point of view, that's an element of the group ring of the free group. Right, same thing. So an element of the free group is a monomial in the generators and their inverses, and then a linear combination is a polynomial, right? Yeah. Thank you. So this is how this is one way to phrase non-commutative star polynomials for general groups. Exactly, thank you. So that's strong convergence. Okay, now I'm going to show you what's really going on with this. So strong convergence and weak convergence. Let's do an example. So Z. So here's like this interval here is the spectrum of the limiting object. Okay, I think I might be assuming Z is self-adjoint. Okay, that's fine. So it's some interval, and then because Z is amenable, the spectrum of the finite dimensional guy is going to be in here. Strong convergence is asking us that this spectrum becomes dense, okay? And weak convergence says something stronger, which is that actually you have weak star convergence of the spectral measure to the limiting object. So I put question mark. That's weird. Like, okay, but actually, I don't care about amenable groups. That's why I'm happy. I don't care about this. Okay. So non-amenable groups. That is really this is the correct picture for me. So now, this is the spectrum of the limiting object, and the spectrum of the finite guy. He can have some values in here, but he can have some values outside now because you're non-amenable. You're able to do this. So strong convergence is now saying, well, you do have to become dense in this, but these guys here outside, they have to get closer and closer and closer to the actual support of the limiting guy, and that's a much stronger thing to have happen. So it says it converges in Hausdorff distance. In other words, if I fix epsilon here, and then outside epsilon I have this red region, the eigenvalues there eventually go away. They're eventually not there anymore. So there are no outlying eigenvalues up to an error, which you can make as small as you want. Now, if the reduced C-star algebra of gamma has a unique trace, which is completely understood now, strong convergence implies weak convergence. Okay. So I'm happy. Now you can tack on weak convergence to strong convergence, but did you really win by doing this? I mean, what's the point? If you have to force strong to apply weak, then I don't know what's the point. Okay. Right. So yeah. So the previous slide is like a very spectral interpretation of strong convergence. There's also an operator algebras interpretation, which I'll give you now. So if you have a sequence of finite dimensional unitary representations of gamma that strongly converge to the regular representation, you can take the product of all those guys. So you get a map from the group algebra into the set of bounded sequences where each element of the sequence is in a corresponding matrix algebra. MNI is the algebra of NI by NI matrices, finite dimensional C-star algebra. Okay, and then this is not very nice, but you can quotient by the sequences that tend to 0. Okay, so you get a map into here. And the purple map here, the diagonal, extends to embedding of the reduced C-star algebra into this quotient object. I used L infinity, but you can use ultra products if you prefer, and I do prefer to use ultra products. But I just wrote it like this, so you can absorb it if you don't know what ultra product is.
Can convergence of 0 of the sequences is by means of an ultra filter, or
yeah, so you can put an ultra filter or not. Okay, something slightly nicer happens if you use ultra filters. Okay, it doesn't really change anything. So the fact that this C-star algebra embeds into this guy, this is an existing property of C-star algebras, which is called the C-star algebra is matricial fields. It appears in paper of Blackadar and Kirchberg. But here's the point. So I'm going to actually, in the next slide, I'm going to tell you other types of problems that relate to such an embedding into an ultra product or something like this, okay? But such an embedding like that does not have to lift up. So it's this property, matricial field, plus a lifting property, plus the fact that you have really representations. Just to have this embedding, you do not have to have true representations, only approximate representations. Okay. So it's matricial field plus something. And I mean, I'm not an expert, but I think that's actually the topic of the next workshop, lifting, right? Okay, so there's a advertisement. If you want to understand when it may, okay, a priori, this lifting is non-trivial, but there may be some scenario that you get in where you know it, you know you can produce it, and that's very good. Okay. So, okay, now I'm not sure the next slide is a good idea, but I'm going to digress for one slide. So, like,
sorry, I have a question.
Yeah.
So you say if it is a strong convergence, then you have this embedding, but it's not equivalent.
it's not equivalent to having this embedding because such an embedding does not have to lift through this.
Yeah, but if I suppose it lifts,
Yeah, it's the same.
it's the same.
It's this plus lifting.
So it's like operating on stability.
No, I'm not saying every map like this lifts. I'm saying there exists a lifted map. Okay.
Ah, okay.
Yeah. I'm trying to relate it to other things. Okay, so this kind of this question, let's just sit on this for a minute though. So like this, I just want to let you know where you are in mathematics. Okay, so what is this? This is there are many things like this. Okay, so I'm going to tell you something. So there are variants of the previous type of embedding, called embedding problem for group fundamental algebras. The existence of non-stochastic groups. Warning, it uses a very different type of ultra product. It's not the C-star ultra product. Okay, so it's not very close, but it is the same shape. We saw a talk, I think, on Monday, which is about selflessness, which is about C-star algebras, and it asks that you can embed. You have gamma, and then you can take a free product with Z, and you can embed C-star red of gamma's free product Z into the ultra power of C-star red gamma in a way that extends the diagonal embedding of gamma. This is called selflessness. And there was a recent breakthrough that this property of the existence of such a map was proved for many gamma acylindrically hyperbolic groups, including, importantly, free groups by Amartam and his co-authors, including Greg, who's here. I'm going to talk about this paper as well, but something similar, but not exactly the same, appeared in my paper with Lars Lauder, where we proved a similar property for, instead of taking a free product with Zs, you take an extension of centralizers, so A is a maximal abelian in a free group gamma, and you amalgamate over this, which means you just add a variable that commutes with everything in A. And we got a similar kind of embedding theorem. It's not written in the paper, but I kind of need to go back to this paper and rewrite it. Anyway, I wanted to relate my talk to this in some way. But these are all the way I presented things, exactly like you said. These questions are not about the way they're written here, not about true representations. Okay? So I really actually care about unitary representations, and that gives things a bit of a different flavor. Okay, so the question I'm going to ask is, for which groups do there exist a sequence of finite dimensional unitary representations that strongly converge to the regular representation? And because it's related to matricial field, but a bit more, we put purity in front. So it's called purity matricial fields, PMF, if there exists a sequence of finite dimensional unitary representations that strongly converge to the regular representation. Don't read this right now. As Ramon explained extremely well in his talk, representations of this form, where you map to a permutation group and then you map using the ni dimensional representation here to uni, are extremely important in the theory of covering spaces. I think Ramon explained that absolutely perfectly. So it's interesting also to ask for these guys, and if you have representations like that strongly converge to the regular representation, I mean, this is me taking liberties, but purely permutation fields, PPF, okay? Like, just to be totally clear, this property implies this property. Okay, it's a much stronger property. These are kind of two extremes. There's lots of things you could do in between. You could replace this representation of the symmetric group by something else. Or you could, something which is actually natural has been used, is just that you ask that your representations have finite image. And that was used by Antoine Song to prove something about minimal surfaces and spheres, which is quite remarkable. So yeah, you could also try to do that.
We do have a PMF which is not PPF.
Yeah, it'll be the subject. The whole talk is about this. Okay. So my question is, which groups have these properties? So yeah, so just, okay, something like this exists already, but not for a discrete group, for like semi-simple Lie group. Okay, so it both motivates the question, but it also is logically related. For we take a semi-simple Lie group, okay, what's the analog of finite dimensional representations? Okay, for me, you take a lattice and you induce a trivial representation from the lattice to G. That's like a finite dimension. I mean, it's finite volume, finite something. Do there exist induced representations like that from lattice to G that strongly converge to the regular representation? And you can choose your poison. So you can put your favorite adjectives to your lattice. You can ask arithmetic, co-compact or not co-compact, non-arithmetic congruence. You probably shouldn't put things that mostly contradict each other. And then you have a bunch of questions, which are very nice questions. In many cases, there are known predictions to the answer of this question that come from either conjectures that are situated in the Langlands program or things in the Langlands program itself. Because the Langlands program is very much about these representations in arithmetic and congruence cases. There are sometimes, it's an interesting theory because there are sometimes obstacles to this happening. One example is Berger-Sarnak. There's another example by Sarnak that if you take a finite index subgroup of SL3Zs, you'll never be able to do this because there are certain representation that non-tempered isotan series that will always appear. So there's part of the theory of representations of semi-simple Lie groups that intervenes. Okay, but I'm trying to ask similar questions for discrete groups where there are not really predictions. So not only does that kind of motivate the question, but there's a direct logical relationship. In fact, you can go by, you can take something you know about the discrete group and learn something about the induced representation. So yeah, so answer to the previous question, for G is PSL2R, yes, there do exist lattices such that the induced representations strongly converge. You can make them co-compact, or all non-co-compact, if you want. This is a result of mine with Hyde. And there's a spectral interpretation of this, which is the following. That there exist compact hyperbolic surfaces with genus tending to infinity, and lambda 1, the first non-zero eigenvalue of the Laplacian, tending to 1/4. That's a spectral version of strong convergence of induced representations. This was a conjecture of Boozer. Genus is a bit misleading. You should think of it as volume. And then, well, we can change the adjectives here. We can make our life a bit harder. We can ask for, can you do this with arithmetic surfaces? Yes, result of Hyde, Lauder, and me. And in fact, any value between 0 and 1/4, 1/4 is the bottom of the spectrum of hyperbolic plane. Any value between 0 and 1/4 is a limit point of lambda 1 of compact arithmetic hyperbolic surfaces, which is my result, to write. But one major question for me, which motivates a lot of this talk, is the same question for hyperbolic 3 manifolds. Does there exist a sequence of hyperbolic 3 manifolds with volume tending to infinity and with first non-zero eigenvalue of the Laplacian tending to the bottom of the spectrum of hyperbolic 3 space? So that's this question from the previous slide in the case of PSL2C. And all progress on the questions, all these results here, they all progress by induction from the PPF property, by induction of representation, by knowing the PPF property for the discrete group. So let's go back to the discrete groups. What was known? So FR is PMF. That's the main result of Hagerup Thorbjornsen, Arnold's paper in 2005. It is the main result.
Question about PSL2C.
Yeah.
If you have lattices, maybe you have sometimes a surface kernel and quotient which is Z. Can you analyze lambda 1 there by means of the
Yeah, I mean,
of lambda 1 of the kernel?
so part of the talk is like pursuing this kind of line of, I mean, I'm going to invite you to, I very much invite you to come and join this quest. Like, we're like kind of stuck and we're looking for ideas. Yeah. let's not jump ahead too far. FR is PPF, that's the result of Borden, Love, and Collins. Like I said, I removed all the randomness from my definition, but it is misleading because everything we know how to prove in a positive way uses randomization, and we cannot get rid of it. So these use random constructions. In fact, for Borden, Love, and Collins, the fact that the result holds in the random model is the main interest of the paper. So I'm also being misleading by saying that they're proving an existence result, whereas they're actually proving something is generic, but they do prove this. Because we use random models, and like I said, we can't really get rid of it. We have no explicit sequence of finite dimensional unitary representations of the free group on two generators that strongly converge to the regular representation. It's embarrassment. What does explicit mean? If you're a computer scientist, then I think the computer scientists believe they've almost answered this question. I should be careful because this talk's recorded, right? Yeah, okay. For me, explicit means like you write me a mathematical sentence, okay? But for computer scientists, it means you write an algorithm for a computer program that inputs NI, outputs some matrices, and the running time should be polynomial on what you put in, but I don't like this answer, so that's not my question. Okay. But even that variant of the question is not completely solved. So you know something explicit when you see it. For example, Morgulis expanders are explicit. Like take matrices in SL3 Z and reduce them modulo P. This is the kind of answer I want. I don't think that's an answer, but yeah. Okay, so that's free groups. So let's try to progress the theory. So the next thing that I was able to do with Lars Lauder was to deal with limit groups. So it's not really the definition of limit group, but it's equivalent. So you can take it to be the definition that a limit group is finitely generated and fully residually free, which means, okay, we know finitely generated. What does fully residually free mean? It means for every finite subset of your group, you can find a homomorphism to a free group that injects on that subset. Yeah, and if you've never seen this before, you might think that this could just never happen, but it's a classical fact that surface groups are fully residually free. And there are many ways to construct these guys. So it's a theorem joint with Lars Lauder that limit groups have the PPF property. And really the motivation for this is that this covers like every surface group, apart from a handful of exceptions that we can also deal with by hand. So surface groups are PPF, and this is very much related to Ramon's talk because you can use this to deal with covering spaces of surfaces. But I want to talk about the proof of this a little bit to give you some ideas. So I mean, there's an obvious thing to do, which is like your definition that goes into your group contains many homomorphisms to free groups. And free groups have many nice unitary representations that do strong convergence. So you pull back the unitary representation from the free groups to the surface group or limit group. Okay, so what's the problem? You can cheat if you read the rest probably, but what's the problem? Well, the unitary representations are doing strong convergence for the free group. So that means like you're getting norms of something that are converging to norms of something related to the regular representation of the free group. This is the wrong norm, right? So you're supposed to be getting something which is related to operator norm in a surface group. So actually all the work is just dealing with differences between operator norms in surface groups or limit groups and the free group. It's not really, in this proof, there's not really anything about finite dimensional matrices. It's just at the level of discrete groups. That's why I can extract that result earlier. Anyway. Okay, so here's how it goes. Let's do general limit groups. So I talked about extension of centralizers before. It means you take a maximal abelian subgroup of your group and you add another variable that in a commutative way extends this maximal abelian, but is otherwise as free as possible from the rest of the group. You can write it as an amalgamated product. And it seems to be like a deep result of Sella and these people that there's some finiteness property that you can obtain every limit group. Every limit group embeds into a finite sequence of extensions of centralizers, beginning with a free group. But for a surface group, you can bypass this step because it's classical how to do this, and you only need to do one extension of centralizer of a free group. So for surface groups, you can bypass this machinery. So now what we do is something very odd. We now take this statement and then reprove fully residually free, right? So, okay, I haven't explained the problem. So you're mapping to free group, you're mapping from surface group, say, or limit group to free group in many different ways. But you don't really know anything about this map, right? In this definition, there's no quantitative aspect. So this map could have extremely large distortion. Like you could take your generators to like just incredibly distorted elements of the free group. And this is very bad if you want to estimate operator norms. So we have to control this in some way. So we now use the bomb slag lemma, which is used to prove that extensions of centralizer are fully residually free, iterate it, and give a new proof. Like not a new proof, no, it's not at all a new proof, but just there's some circularity, but we prove that this extension of centralizers is fully residually free. But then we go into this proof and we make it quantitative. Okay? So we use this deep finiteness result, and then we go through the levels of this extension of centralizers and we make something quantitative. So we prove a quantitative version of the bomb slag lemma, which gives a quantitative version of this for every limit group. And then we can combine with like just kind of standard technology from estimating operator norms in the regular representation of the free group, which is called high group inequality or rapid decay. Yeah.
And so this problem of different groups giving you different norms does not occur when you pass to subgroups? Because here you embedded gamma somewhere else, so.
No. When you pass the subgroup, you have the same norm.
That's fine. Okay.
Yeah, because L2, like if lambda is inside gamma, L2 of gamma splits as a lambda module. It splits as a direct sum of copies of L2 lambda, right? So the operator, yeah, exactly. Yeah. But you can. Okay, yeah, there are different ways to get around that anyway. Okay, so yeah, I just wanted to give you some ideas about this. But anyway, so this idea is sort of it could be taken and used outside the context of strong convergence. It seems to be good. Okay, so what comes after limit groups, or what can we prove next? The next category of group I want to talk about is right-angled Artin groups. There are different ways to motivate this. Like one is, okay, what is a right-angled Artin group? You have some number of generators, and the only relationships are that some of them commute. Okay, so one way to motivate it is that it interpolates between free group and a free abelian group. But okay, I think you'll see my motivation in the next slide. But really, there are like fundamental objects in geometric group theory, and it turns out that yeah, once you prove something about right-angled Artin groups, you prove it for many groups. Okay, so okay, we'll come to that in a minute. The theorem is that all RAGs are PMF, and the proof is by random matrix theory. Right, so we developed a model of random matrices to deal with right-angled Artin groups, but then of course, if you come up with something good, then you find out that someone else already did it. So this model was already written by Charles Worth and Collins. I won't explain the model because it's a nice idea. So I want to get some finite dimensional unitary representations of right-angled Artin group, and I want them to be representations of the right-angled Artin group. So when two generators commute, the images should commute, right? But I also wanted to have a chance of strongly converging. So if two guys are not supposed to commute, or like they're supposed to be free, then they should become strongly free in the limit, right? So I have to address both of these things. So what I'll do is I'll take like a vector space of large dimension. I'll take its tensor product with itself some number of times. So now I have this like tensor structure. You can think of it like, you know, a product set with different indices, or yeah, you have different indices. So now what I do is each of my images of generators will act on some factor of this product space, right? So I'll choose some subset of the indices, and this image, this unitary will move this factor, and this factorization of the tensor product, and it will do nothing to the complementary factor. But it will not itself preserve the tensor structure of its own factor. It'll forget it. So it'll act as a random GUE or a random unitary in this factor itself will be a tensor product, but it will not remember that this is a tensor product. Okay. And then all you have to do is make sure that your GUEs overlap if they're not supposed to commute in the limit, and they don't overlap. If they don't overlap, then they just commute. So this is a nice idea. I mean, well, we didn't come up with it. We proved the strong convergence in this random model of GUEs. There's a trick that you can use to go from GUEs, which are random Hermitian matrices, to random unitary matrices. Yeah, and there are some really nice ideas in the proof. It's the same as last time. It's like somehow the proof is better than the theorem. Like, hopefully someone can take something away from this. The proof is based on this funny tensor GUE model. Then there's an intermediate step which removes all randomness but produces operators, very large matrices, but with entries in free Toiplet algebras. And there's some ad hoc analysis of these matrices with operator entries. And then the strategy of the proof is to actually use a universality theorem for Toiplet C-star algebras that says as soon as you have like creation and annihilation operators with commutation relations given by the same commutation relations as the RAG, you have a unique C-star algebra which is generated by these guys as long as they satisfy something non-degenerate. And that's very powerful because by like ultra product argument you can construct some limiting C-star algebra, and then once you prove that the C-star algebra has generators with the right commutation relations, then it automatically has to be the C-star algebra that you want it to be. Okay, so that's like a sort of rigidity and infinity. So what I presented as the GUE model, ours is a massive hack, and the clean version of this GUE model was proved to strongly converge by Chen, Garza, Vargas, and Van Handel. Yeah, and they cleaned our model in various ways and proved strong convergence. Okay, so yeah, it's strange. And at the end result is that every single right-angled Orton group has a sequence of finite-dimensional unitary matrices that strongly converge to the regular representation. Okay, so I think the question has just come up. PMF is preserved by going to subgroups and finite index over groups. Okay, these are not very hard to prove. So, in particular, anything that virtually embeds into a RAG is PMF. And it turns out that many things virtually embed into RAGs. One important example is hyperbolic three-manifold groups. So they're PMF, and this is a whole story with many, many works. So Egel, Bergeron, Wise, Hagelin, Wise, and Wise. The last Wise is for the non-compact case. Okay, and then we know that once we prove something about the discrete group, we get something for the locally symmetric space. This is slightly unsatisfying because we have PMF, not PPF, but we still get something. If you give me a compact hyperbolic three-manifold, there's a sequence of flat Hermitian vector bundles over that hyperbolic three-manifold, whose dimension tend to infinity, and the natural Laplacian has a spectral gap that tends to lambda 1 of H3, which is 1. Hyperbolic three-manifold groups are PMF, and so is anything else that virtually embeds to a RAG, and there are many theorems. So I'm not doing any work at this point, other people are doing work. Hagelin Wise proved the Coxeter groups virtually embed into RAG, and Wise proved one related groups of torsion do as well. Okay, and then there are theorems like this I probably don't even know. But unfortunately, yeah, so like really, the question I really want to solve is about hyperbolic three-manifolds and covering spaces. And so I want to improve this M to P. And then I improve this to not vector bundles but covering spaces. But sadly, I cannot proceed on this line because RAGs are not PPF. So F2 cross F2 is not. It's a fun exercise to do this, or you can look up the solution the survey wrote. But that just means I cannot get what I want by virtually embedding into the RAG. Also, a very bad thing is that once but when I apply Egel Y's, I actually know nothing about this embedding. Like I cannot get anything about it. But I still hope that hyperbolic three-manifold groups do have this PPF property. But I'm kind of out of ideas, so ideas are very welcome, like using virtual fibering or. But hyperbolic three-manifolds are hard. Like we don't even know. This is a weak convergence question, but we don't even know whether you take a hyperbolic three-manifold and you look at all the degree n covering spaces of it. There are finitely many. Okay, so you can pick one at random. We don't know whether this random model converges to hyperbolic three space in the sense of Benjaminian tram, meaning you pick a random ball, if you fix R and you take a random ball of radius R in the random guy, does it look like a ball of the same size in H3 with probability tending to 1? So this is also a very nice question. But it's sort of, we can't even prove weak convergence in this model, so strong convergence is very far away. Okay. Any questions? Maybe I should hide this slide. So the program is to deal with all groups. Maybe every group is PMF. Well, that's definitely not true because there are like groups with no representations. Right? I didn't really talk about this. Yeah, I should take my own medicine as well. Like I asked for examples, but how do we know how do we know when groups have unitary representations? Could just be that something is not PMF because it just has no finite dimensional unitary representations, right? But this is kind of don't want to think about this. So one class of groups that have many finite dimensional unitary representations are residually finite groups, because they have many homomorphisms to Sn, and then exactly this type of representation I showed before, then you get this. And they sort of get more and more complicated by... Residually finite is the same as fully residually finite, so you can inject on larger and larger sets. And then they get more and more complicated. So you have many, many interesting unitary representations of residually finite groups. So I'm just saying, I'm really in the category of residually finite. I'm thinking about residually finite groups. So this is a sad point of this theory of strong convergence. There are lots of rigid groups for which we know all the finite dimensional unitary representations, and in principle you can write them down. So that, I mean, it should be a happy face, but the sad thing is, like, we can't, even if you write it down, like Morpheus expanders, you cannot decide, we don't have a way to decide whether it's strongly converged or not. Either yes or no. So, like, SL3Z is still open. Yeah, every single finite dimensional unitary representation arises by reduction to, congruence reduction to SL3Z mod MZ. And then, in the context of strong convergence, you may as well choose theta to be irreducible, but then choosing a finite dimensional representation theta of SL3Z mod MZ to UN. By Chinese, if you want to understand these representations by Chinese remainder theorem, you can reduce to prime powers, and then, yeah, you can understand everything in principle. But we can't decide. We can't decide if any of them strongly converge.
They do converge in trace.
Yeah, I know. Yeah. It's very annoying. But we use the strategy of knowing them all to prove that SL4Z is not PMF. And the way it works is actually just proving something completely algebraic, which is that every non-zero finite dimensional unitary representation of SL4Z has a non-zero SL2Z invariant vector. And SL2Z is this. So that's something you prove, and the strategy is going to prime powers and actually taking a generic representation and working with it. Okay, but why does this theorem imply this? So if the rho I, if you have a sequence of finite dimensional unitary representations that strongly converge to the regular of SL4Z, this goes to subgroups by exactly my answer to your question, that L2 of, yeah. This goes to subgroups, so you're strongly convergent when you restrict to SL2Z. The SL2Z is not amenable, so its regular representation has a spectral gap. So since we're converging to that strongly, the finite dimensional guys have to have a spectral gap on SL2Z. but there's an invariant vector for SL2Z, so this is just completely cooked. Right? Yeah, I mean, everything is written in our paper, so if you didn't follow this, you can read. The sad thing is that the second theorem is false. We know it to be false in SL3Z. But for only one particular sequence of representations. But as I said, we cannot look at this and see if it does strongly converge or not. Okay. This was explained to us by Deline. His name should be here.
Can you say more about this particular?
It was, I mean, once you know it exists, like I think Mikhail did this, once you know it exists, then you can look at the character table for SL3, like Z mod P, right? And then deduce from the character table, but like, Deline was able to explain from the point of view of Deline-Lustig theory, like why, I can't remember exactly what the description is, but it's one of the extreme ends of Deline-Lustig theory that gives it.
The ones that are the most difficult to describe algebraically. I have three families for SL3Z, three families of representations. Two are easy to understand, and the third one is hard for me. And this is the one. If it helps.
Is it P?
Yeah, yes, sorry, I wasn't being precise. Yeah, it's false in SL3Z when you reduce modulo P, and then it was already false there. And so this was basically the talk, but there's a homework, which is like everything else. Okay. So like I mentioned, SL3Z is very annoying given what we know about it. This is even worse. This is sort of even worse. Everything of this type. I'm not sure if this belongs exactly here, but I am very curious about this as well, this case. But the problem is I don't understand it well. Because it's, yeah, somewhat in between different categories of things. Any hyperbolic three-manifold group being PPF, we know PMF by the RAG stuff. Any hyperbolic three-manifold group being PF, having covering spaces with, one nice one is the figure 8 null complement, which is a free bicyclic group. This is describing an automorphism of F2. I hope it's clear what it means. If you can give me any free bicyclic group, which is PPF, I'll be happy. Complex hyperbolic lattices. I mean, some of these things we just have no way to begin. Like for hyperbolic three-manifold groups, we use ego-Ys. It just doesn't seem to be anything like that here. So we're just completely stuck. Braid groups is actually, I think there's some room to do something here because there are some known unitary representations that come from like Yang-Baxter equation. There's this thing called R matrix. So there's a parametric family of unitary representations of braid groups, which is quite nice. Mapping class groups have no idea, etc., etc. I mean, I don't think it's helpful to phrase things like this rather than for particular groups, but it is curious. Does any property T group have PMF? And this is your homework, and I'm done. Thanks for listening.
Thanks a lot. Other questions?
Is there some kind of compactness principle saying that sometimes take a sequence, some criterion that would say that there would be some limit, maybe not a regular representation?
Yeah, you can always do ultra product. You can always take an ultra product. So yeah, you can always extract a C-star algebra. This is interesting because it gives you a technique. Where was my thing? Oh, it was software. If you use ultra filters, you can always take C of gamma, embed it into the ultra product, and then take the C-star algebra that it generates. So you always have a C-star algebra, and this is quite nice because if you know structural theorems about C-star algebras, you can apply them here. But yeah, there's always a limit after you choose an ultra filter on N, and it's a C-star algebra.
I have
question on your result. You were louder on the extension of centralizer. Can you say a few
So,
words?
yeah, this one here. So it's essentially what we prove in our proof.
So you're taking what? You're taking, so gamma is a free group, you take a free product, and what is A?
A is a maximal abelian.
Okay.
Actually, let me.
It's just it's a cyclic, yeah. Just another Z, right?
Yeah.
Sorry?
Lots of proper power.
Okay.
I want to show this example. This is surface groups being fully residually free. So this is a surface group. So I'm going to take extension of centralizers of, I'm going to take extension of centralizers of the commutator of A and B. So now I'm going to have two generators, A and B. This is a free group, but I'm going to add a variable t, such that t commutes with the commutator of A and B. That should be another bracket. So now I have a map from gamma 2 to this, let's call it E. It's E, where I send A to A, B to B, C to B, and D to A, except no my notation. I conjugate by T. Okay. And this is actually an embedding. Okay, so does this answer the question of what is extension of centralizers? So I've extended the centralizer of the maximal abelian, the cyclic group containing the commutator of A and B. And then the proof that E is fully residually free. Proceeds by sending A to A, B to B, and T to a high power. Well, what does T have to map to? It has to preserve this. So it has to map to a power of the commutator, and so it does. And then we let Q's go. Yeah, I wasn't sure if I would have time to do this example, but I think it's nice. Is it clear? So the proof that this embedding works is by normal form for amalgamated products. And then the proof that this works is the Baumslag lemma.
Actually, have 2 minutes left in the talk, so room for questions.
Yeah?
So you said that F2 cross F2 cross F2 is not a PPF.
Yeah.
Is that easy to see?
Yeah, so we use the argument we use for SL4Z and SL2Z. So F2 is not amenable, so it has to have a spectral gap in its action, right? So what we're going to have for F2 cross F2 cross F2, if it is PPF, is a permutation representation, and we're going to remove only one dimension, right? So for the F2 to have a spectral gap, it has to act transitively. And it's the same for all the F2 factors. But let's take the first two F2 factors. They commute with each other. So they're not permutation groups. In the image, they're permutation groups that commute with each other, and they're transitive. And the only way this can arise is if there's some auxiliary group H, such that the first F2 factor is mapping to H, and then H acts on itself on the left, and then the second one is mapping to H, and H is acting on itself on the right. But then where does the third F2 go? It cannot. So yeah, anyway, this is the proof. And so there's a theorem of finite group theory that two commuting transitive permutation representations are this form.
So for 2 it's okay.
This is a good question. So For 2 from the same argument, though, you learn that if it's going to work, it basically has to come from Cayley graphs.
Can you repeat the question?
F2 times F2.
For F2 times F2, if you repeat this exact argument, you learn that the strong convergently permutation representations have to come from Cayley graphs, and this seems really hard. It contains the, I think it essentially contains the question of viewing whether random Cayley graph of Sn is a uniformly expander, at least. Right, so, but it's like a 2-sided version. And then F3 cross F3, there's another funny. So see, the proof for F2 cross F2 seems to almost work, right? Because here's why it almost works, because there's an F2 acting on some group H on the left, and there's an F2 acting by some group, the same group H on the right. But then there's also diagonal F2, right? And then L2 of H, you have some V tensor V check. So you have an invariant for the diagonal for every irrep in every irrep of H. This proof is wrong because there can be a twist. The two F2 actions can be twisted. But what if there's only one orbit? Like what if you know Weigels or something like this? Then there's something. So F3 cross F3 is even worse. Because you have something like Weigel for F3, but not for F2. Yeah, okay. It's very weird and subtle.
Let's thank the speaker again.